We're ready to start talking about the last section in this chapter in multivariable calculus. In this section, we're introduced to two new coordinate systems, the cylindrical system and the spherical coordinate system. We already are familiar with two coordinate systems, the rectangular or Cartesian system, which is the one we've been working with up to this point. You also learned in Calculus 2 about the polar coordinate system, which was a two-dimensional system. Now, there are lots of things in the real world that are not well described by the rectangular coordinate system. For example, a DNA molecule has a helix structure, which is a spiral in one direction, which means that it's not well described by rectangular coordinate systems, which are based on rectangles. The same is true for describing the volume of some kind of domed shape, or for computing, say, how oil moves through a pipeline. For these situations, we need a different kind of three-dimensional coordinate system. The cylindrical coordinate system is actually an extension of the polar coordinate system into three dimensions. What it does is it takes the r theta polar coordinate system, typically the xy plane, and extends it into 3D by adding a third variable, which is the z variable. Now, it could be applied to the other coordinate planes as well, in which case I could project r theta onto the yz plane, and then my additional variable would be x, which is coming out of the yz plane. The spherical coordinate system, as it's named, is based on a sphere, while the cylindrical coordinate system is based on a right circular cylinder, what we typically think of as a cylinder. Let me share my screen with you, and we'll go ahead and get started with a more detailed look at these two new coordinate systems. We're going to start with a look at the cylindrical coordinate system. There are two figures here on the screen. In the left figure, you see a point projected in three-dimensional space. In the rectangular system, this would be given by the ordered triple x, y, and z. If we cast a shadow of the P point down into the XY plane, as if we're holding a flashlight pointing downwards but parallel to the Z axis, we get a shadow cast underneath it down here in the XY plane. Then we can measure, starting at the positive x-axis and rotating counterclockwise, as we do in the polar coordinate system, we can measure the angle of that point between the positive x-axis and where its projection into the xy plane is. Then we can measure the distance from the origin in the xy plane to the projection of the point. Remember, the projection of the point is directly under the point projected into the plane where we're applying the r theta coordinate system, or the polar coordinate system. What this does is this creates a sort of right circular cylindrical shape, which you see in the image on the right. Again, you have a point given in three dimensions up here in space. It casts a shadow onto the xy plane, and we can measure how far that shadow is in terms of theta radians from the positive x-axis, and r, the radial distance from the pole or the origin to the projection of the point. Now, this gives us a new way of describing the point in cylindrical coordinates, where we give r, theta, and z. R and theta are typically in the xy plane, but again, they could be extended to apply to the yz plane or the xz plane. This gives us the coordinates r, theta, z. When we're looking at it, this is a representation of three-dimensional space, but in terms of things that are well described by cylindrical shapes, or that move along cylindrical shapes. The definition then is the ordered pair r theta being the polar coordinates of the point's projection into the xy plane, And z is just the normal, usual rectangular coordinate system, z coordinate. This creates a right triangle, which normally lies in the xy plane, since normally we're using the xy plane for the r theta plane. The length of the hypotenuse is the radius r, and theta is a measure of the angle formed by the positive x-axis and the hypotenuse, just as in polar coordinates. Again, z describes the location of the point above the xy plane. And again, we can apply this to either the yz plane or the xz plane. Our primary goal in this section is just to learn how to convert from rectangular coordinates to cylindrical, from cylindrical to rectangular, from cylindrical to spherical, from spherical to rectangular, rectangular to spherical, just to go back and forth between these three different types of coordinate system. In this first set right here, we're going to see equations which will allow us to convert from cylindrical coordinates to rectangular coordinates. How do we know that we're converting from cylindrical coordinates to rectangular? On the left side, you'll see that we're solved for the rectangular coordinates x, y, and z. X, as in the normal polar coordinate system, is r times cosine theta. That's using right triangle trigonometry from the right triangle, which is projected by the point down into the xy plane. Y, as it normally is in polar coordinates, is r sine theta, and z is just the normal z coordinate. So how could we go backwards? How could we go from the XYZ rectangular coordinate system into the cylindrical coordinate system? For that, we need these relationships, which you see below. In these relationships, recall that the projection of the point down into the plane creates a right triangle. Let's take a look again at the picture so we can see this right triangle. In the image on the left, you can see that the r is the radius of this particular one and the hypotenuse of the right triangle. Note that the extension along x and the parallel movement to y must be at a 90-degree angle, since x and y are at 90-degree angles. And this creates a right triangle. And we know then that x, since this angle here between the positive x-axis and r, moving counterclockwise, is theta, then we can have x as r cosine theta, the adjacent side to that angle, and y is r sine of theta. That's using right triangle trigonometry. It also means we could use the Pythagorean theorem, x squared plus y squared equals r squared. We also can find the angle theta by taking the tangent of the angle as y over x, and then solving for theta using the inverse tangent function, arctangent. When we do that, though, we'll have to be careful to make sure that we get the point in the correct, into the correct quadrant or the correct octant, because it will give us a value between negative pi over 2 and pi over 2, and it may give us the same tangent value, but it may not be the correct angle. So we'll have to be a little careful about that one. So that gives us two of the three equations that are needed to go from the x, y, z coordinate system into cylindrical. X squared plus y squared equals r squared. The tangent of the angle is y divided by x. And the third one is, again, that z is just itself. Note that because of the definition of the radius, r is considered to be strictly non-negative here, and theta is going to be the arctangent of y over x. We could also use those equations. We're going to limit theta to being between 0 and 2 pi, though theoretically it could be between negative infinity and infinity, but we're going to limit it to 0 to 2 pi. And we'll use the coordinates x, y, z to determine which octant or quadrant it is lying inside of. Theta is the angle projected into the xy plane, so we really only need the quadrant that it's in. And remember that tangent is positive in quadrants 1 and 3 and negative in quadrants 2 and 4. Let's take a look at the traces in the cylindrical coordinate system. If we let c be a constant in rectangular coordinates, if I write the equation x equal a constant, then I'm talking about a plane which is parallel to the YZ plane stepped forward at, say, x equal 2. So it's the entire plane where everywhere on the plane the x value is 2. Y and z can be anything, but x is always 2. If I use an equation y equal to a constant, then that means that the y value is always the same value. Let's say it's -1. So I've moved 1 over in the left direction. Then I have to stay in the plane, which is parallel to the xz plane. But as long as y is -1, then that will give me that plane parallel to xz. And finally, if z is equal to a constant, that will give me a plane that is parallel to the xy plane at height z equal to whatever the constant is. Now, let's take a look at these images of the three situations that we have. In this first situation right here, you can see that we are visualizing the YZ plane. This is x equal to 0. And in the second one, we are visualizing the XZ plane where y is equal to 0. And this one, we're visualizing what looks like the plane z equal to 2, actually. So if I'm looking at that plane, I've got z equal to 2, and it's parallel to the XY plane. If we look down here in the cylindrical coordinate system, and remember the cylindrical coordinate system is given in terms of r, theta, z, so polar plus z. If I fix r to be a constant, then this will give me the series of points that are a fixed distance from the z-axis, which produces, of course, these vertical circular cylinders. Now, what if I were, instead of to fix r to be a constant, I were to fix the angle theta to be a constant? Remember, theta is measured counterclockwise from the positive x-axis out. If I do this, because it's measured from the positive x out, instead of giving me an entire plane, it gives me half of a plane. So the plane starts at the z-axis and extends along the direction towards between the radius and the positive x-axis. And that would be theta equal to some constant, like say theta equals pi over 6. Where's that going to be? Well, it's going to be about 2/3 of the way through octants 1 and 5. And it will be that half plane, but it won't extend behind the screen. If we take a surface z equal a constant, it produces the same type of shape that it produces in the rectangular system. It produces a plane that's parallel to the xy plane. So it's exactly the same in both systems. In CalcPlot 3D, we'll use implicit surfaces to plot something like theta equals pi over 4. And we'll use a function such as r equal to f of theta z to plot cylindrical coordinate equations. So you'll see when you click on select, you have a choice implicit surface to get theta equal pi over 4. And if you want to plot something in terms of theta and z, it's this first function right here. The second two are not active yet. That's why they're grayed out. But you can write r as a function of theta and z. And it's not a big handicap not to be able to use the second two, because we can always use the implicit surface equation to get the equation for any surface in 3 dimensions. Let's take a look now at plotting theta equal pi over 4 in CalcPlot 3D. I'm going to add a screen and turn on CalcPlot 3D. There's the typical home screen. I'm going to turn that off, and I'm going to select an implicit surface. It always gives me an option, but I don't want that option. So I'm going to erase that option by hitting delete. I want theta equal some constant. which is going to give me a half plane. And I want theta equals pi over 4. So I'm going to click down here where the theta symbol is, or you can type in theta. And then I'm going to enter theta equals pi divided by 4. And you can represent pi with pi, right? Remember that you have to hit enter while clicked into the box in order to get it to execute. And now we can see that we do indeed have half of a plane. It does not extend in the backwards direction. It's just the forwards direction, going up and down and coming out at that angle forever, right? So if we project into the XY plane like this, you can see that the plane becomes this line right here, where the angle between the positive x-axis and the line is always pi over 4. So the angle theta is right here. Let's now take a look at converting from cylindrical to rectangular. And remember that plotting in rectangular coordinates requires you to move along a line parallel to one of the axes. And we use sticky notes with units marked off in order to help us do that. Plotting in cylindrical coordinates means first you have to find the spot in the XY plane, or whichever plane you're projecting r theta onto. Once you've identified where the point is in the plane, the shadow cast by the point, then you move parallel to the z-axis to plot the point. In this case, we can see that point R has cylindrical coordinates given by 5 pi over 6 and 4. Pi over 6 is roughly 0.52 radians. So when we're looking at this, you can see that what we do first is we go out a distance of R, which would be 5 from the origin, at an angle of pi over 6. We plot the point in the XY coordinate plane, and then we move parallel to the z-axis up 4 units. Let's go ahead and describe this point in terms of the rectangular coordinate system. What would we come up with in the rectangular coordinate system? When we're doing this, remember that our relationships are x is equal to r cosine theta and y is r sine theta, coming from polar coordinate systems, and z just stays the same. So coming over here now, we have the equation x equals r cosine theta, and we have y equals r sine theta. And we know that up here, this is r, this is theta, and this is z. So r is 5, theta is pi over 6, and z is 4. I can plug these values into my equations, and I get 5 times the cosine of pi over 6. The cosine of pi over 6 is square root of 3 over 2. So I get 5 square roots of 3 over 2 for the x coordinate in the rectangular system. Now I'm going to do something similar for the y, and I'm going to have r again being 5. And this time I take the sine of the angle pi over 6, which is 1/2. So I get y is equal to 5/2. Now the z coordinate doesn't change between rectangular and cylindrical, so it's still 4. So my point becomes 5 square roots of 3 over 2, comma, 5/2, comma, 4 in the rectangular system. This is what it looks like in the cylindrical system. Notice they look different. How do you know you're in one and not the other? You have to be told. You can't tell by inspection. Just because it has a pi in it doesn't necessarily mean it's in cylindrical. It could be at the value of 0.52. You have to be told which system you're in. Let's now go ahead and move on to converting from rectangular to cylindrical. I almost jumped ahead to spherical. So in this case, we want to use the opposite relationships the Pythagorean theorem, x squared plus y squared equals r squared, and the relationship that the tangent of the angle theta is y over x, and z, of course, is still going to stay z. So this is the point in Cartesian or rectangular coordinates. So this is x, -8, y is 8, and z is -7. Let me get that y a little higher so it doesn't hit the 8. So I want to convert. The first thing I need to go to cylindrical coordinates are given in terms of r, theta, and z. I already have z, which is going to stay -7. I need r and theta. To get r, the first thing I'm going to do is square the x and square the y, and that will give me r squared. So this is going to give me -8 squared plus 8 squared, which gives me 64 plus 64, or 128. And when I apply the square root, I can get that r is either 120, the negative root of 128, or the positive root. We typically always take the positive root. So this is basically going to give me 8 square roots of 2. Now let's find the angle theta. To find the angle theta, we want to use the relationship that tangent of theta is y over x. So we'll come up here and we'll write that equation down. Tangent of theta equals the y coordinate divided by x coordinate. So theta is the arctangent of y, which is 8, divided by x, which is -8. So I have theta as the arctangent of -1. So I need the angle whose tangent gives me a -1. Arctangent's defined between -π/2 and π/2. Now, because it's negative, it's got to be backwards in quadrant 4. But because the x and y coordinates magnitudes are the same, they're both 8, then I know it's a multiple of π/4. But it's negative, so it could be in quadrant 4 or quadrant 2. So it could be -π/4, or it could be 3π/4. So I need to determine which one it is. To do this, we're going to look, basically, since I'm looking for theta, which is in the xy plane, I just look at the x and y coordinates. If the x is negative, but the y is positive, which quadrant are you in? Well, you've gone left and up, so you're in quadrant 2. The angle in quadrant 2 that has a tangent of -1 is going to be 3π/4, not -π/4. So this one would give me the answer of -π/4, but the actual angle I'm looking at for is the one that is pi radians opposed to it. So my theta is in quadrant 2, 3π/4. So again, let me go over how I did that. I looked at the x and the y coordinates. X is negative, y is positive. So if x is negative, it's behind the screen. Y is positive, it's that way. The positive x is here, so I've gone past the screen, so I'm into quadrant 2. So in quadrant 2, the angle, equivalent angle, would be 3π/4. And then I simply write the coordinates in cylindrical as 8 square roots of 2, 3π divided by 4, and the z stays -7. And that becomes my solution. Let's take a look at identifying the different surfaces that we've talked about in the cylindrical coordinate system. We talked about a half plane, which is given by theta equal to some constant. So again, the angle between the positive x-axis and the half plane is the constant that theta is equal to. And it only extends in half the direction, but r and z are allowed to vary. When we hold the radius constant, but we allow theta and z to vary, the result is a circular cylinder. And this is where it gets the name cylindrical coordinates. So in a case like this, I want to plot something like r equals 3. I go out to calc plot 3D, select that function, r as a function of theta and z, and then I can plot r equal 3. Notice that when you do that, it will open up a screen which will ask you what theta goes between and how far up and down along the z-axis you want to plot. And you do want to make sure that you get far enough out that you can see it. So let's take a look at this one coming off to the side. So when we're looking at this one, again, it's plotted by clicking select and coming down to r equals a function of theta and z. When you do that, it will open up a box that says r equal, and you can type in whatever the equation is, in this case 3. I do want theta to go all the way around, so I say 0 to 2 pi. And I want to make sure I have enough of it to make a good picture. So I said -4 to 4. Now, if I had stuck with the original, which was -2 to 2, I wouldn't have seen anything. And the reason is because the radius is 3. So it's not going to plot until you get past 2. So make sure that you choose values that get past your radius. If we have an equation, r squared plus z squared equals c squared, the result of that is a sphere centered at the origin. And you can see the picture right here. Now, how would we plot r squared plus z squared equals c squared in Calc Plot 3D? To do that, we would use an implicit surface since we're plotting the entire equation. If I solved it for r, I would have to split it into a positive root and a negative root and plot them separately, but it would give me the sphere. But now you know how to get a half sphere, right? A hemisphere would be solving for r, and the upper hemisphere would be given by the positive root and the lower hemisphere by the negative root. So when you're looking at these, you will come out here and you'll have r squared plus z squared equals 25. Now, normally when we plot an implicit surface, these are x, y, and z values. But Calc Plot 3D will detect that you have r squared and z squared in the equation after you hit enter, and it will automatically change these to reflect the cylindrical coordinate system. Make sure, since this is a sphere of radius 5, that your r value extends past that point, that you're going all the way around 0 to 2 pi, and that you're showing both the upper half and lower half of the sphere by extending the z values as well past the radius, right? So this is the equation, r squared plus z squared equals some constant squared. If we have r equal to z, the result turns out to be a cone, a double napped cone. So it's got the upper part like an ice cream cone and the lower part like an ice cream cone. So this, again, we will use the function, r is a function of theta and z, and make sure that theta goes from 0 to 2 pi so you get all the way around the cone. And again, you want to extend your z values both up and down so that you're getting both naps of the cone. And you can see the picture of the cone right here. Let's now talk about spherical coordinates. In the spherical coordinate system, we're no longer based on a cylinder, a right circular cylinder. We are instead based on a sphere. Now, the cylindrical coordinate system is not as difficult as the spherical. Spherical tends to be more challenging because instead of using two distances in one angle, such as in the cylindrical system, it uses two angles and one distance. Plus, the distance that it uses is not parallel to any of the axes, x, y, or z. So they're going to use rho, theta, and phi. And you can see them spelled out here in the lecture notes. Rho is R-H-O, it's the Greek letter R. Theta, T-H-E-T-A, and phi is P-H-I. Now, phi sometimes looks a little bit different. So you can see that phi, depending on the font that's used, either resembles a 0 with a line through it, or sort of a curving 0 with the diagonal slash going down through the bottom. Both of those represent the same variable of phi. So let's talk about what rho, theta, and phi r. Now keep in mind that some textbooks call rho r because, well, it is the Greek letter r, but our textbook does not do that, so we won't do that. We're going to reserve r for the radial measure of the projection of the point into the xy plane. So r will be for the polar coordinate system. And we're going to use phi strictly for the spherical system. Rho represents the distance from the origin to the point in three-dimensional space. So this would be the straight line distance from the origin to the point in three-dimensional space. Theta is the same for cylindrical or polar coordinates. It's a measure of the angle of rotation from the positive x going counterclockwise to the projection of the point, the shadow cast by the point down into the xy plane. Now, what is phi? Phi is the second angle in spherical systems. Phi is, let's suppose my point's over here and my head and body are serving as the z-axis. So positive x is coming out towards you, positive y is going this way. My point is over here. Phi is the angle that you have to move from the positive z-axis down to get to the point. So this angle right here that we're moving through, this angle here, that is phi. Now, to get to the point, if it's up here, of course, phi will be between 0 and pi over 2. If phi is below an octant 5, then it will be greater than pi over 2, but less than pi, because if I went around over here, well, then I've got a shorter angle to get there. So the angle phi is always between 0 and pi. Theta, again, could technically be anything, but we typically write it between 0 and 2 pi. Phi has to be between 0 and pi. Let's take a look at a picture to make this a little bit more clear. Not sure I can get it all on there at once. So here's my point P in three-dimensional space, and it casts a shadow down into the XY plane on the floor. And this is the point Q. So Q is directly under P. So my flashlight is shining down, pointing towards the negative Z axis, parallel to Z. Theta is measured from the positive X axis to the projection of the point in the plane to Q. R, of course, would go from the origin out to the point Q, but rho goes from the origin to the point P in three-dimensional space, and that's the one I use. Phi is the angle from the positive Z axis down to this straight line distance from the origin to the point. Let's take a look at what it looks like on a sphere so you can see why this is called a spherical system. And the one on the left, you can see that if you took this rho value and you allowed rho to be a constant and you spun rho around in all possible directions, varying theta and phi as much as possible, it would create a sphere. And that's where it gets the name spherical system. So again, coming over here, we have the rectangular coordinate system, x, y, z. We have the cylindrical system, r, theta, z. And now we have the spherical system, rho, theta, phi. And you can see the relationship right here between the different points. Let's take a look at a projection down into the YZ plane. So if we're looking into the YZ plane, which would be like looking at it this way, instead of down into the XY, if we're looking at it this way, we have a relationship between R, which is that coordinate in the cylindrical system, and rho, and the angle phi and Z. Namely, these two lines here are parallel to each other, and we can consider rho to be a transversal cutting two parallel lines, which means that alternate interior angles are equal, which means that in this right triangle that you have right here, remember R is in the XY plane, so it has to be at a right angle to the Z axis. So this is a right angle. Then we have the relationship that you see here, namely that r squared plus z squared equals rho squared. But r squared is x squared plus y squared. So now I have x squared plus y squared plus z squared is rho squared. All right, what else do I have? Well, I also have the cosine of phi is the adjacent side z divided by the hypotenuse rho. So if I multiply rho then by it, I can come up with an expression for z. So z is rho cosine of phi, and r is rho sine of phi, the side opposite to it. And this gives us a way to relate the two together. And you can see in the image on the left that I've labeled all the different sides so you can see the relationship. Remember that my point is P in three-dimensional space. Q is the projection or shadow of the point in the XY plane. R is in the XY plane from the pole or the origin out to point Q, the shadow. But this is also equal to rho sine of phi. The distance, straight line distance from the shadow up to the point is z, which is rho cosine of phi. And we also have that x is r cosine of theta and y is r sine of theta. These relationships will allow us to convert from any of the systems to the other. Let's now take a look at converting the spherical to cylindrical and cylindrical to spherical. So if I'm starting with spherical, then I'm starting with rho theta phi. And if I have rho theta and phi, and I need r theta and z, then I can use the relationship that r is rho sine of phi to get r. Theta stays the same, and z is rho cosine of phi. And that will convert from the spherical coordinate system into the cylindrical. To go in the reverse direction from cylindrical to spherical, that means that I'm starting with r, theta, and z, and I need to get back to rho. Well, r squared plus z squared is rho squared, so rho is always a positive distance coming from the origin to the point, and that would be the square root of r squared plus z squared. Theta stays the same, and I'm using the same relationship here, but solving for the angle phi using arc cosine. Now remember, phi is the angle between the positive z down to the point, the line from the origin to the point. And it has to be between 0 and pi. It makes sense to use arc cosine, this relationship, since arc cosine is defined between 0 and pi. That way we know that we're getting the right one, and we don't have to worry about which quadrant it's in like we do with arc tangent. Let's now look at the relationship between spherical and rectangular. Spherical and rectangular, remember that x is r cosine of theta, and y is r sine of theta, and z is just z. Now r, remember, r is rho sine of phi. So let's add that up here, rho sine of phi. It looks sort of like, rho looks sort of like a P, but it's rounded on the back. It's not a ball and stick. And that's one of the symbols for phi. The other way of writing it is with a 0 with a diagonal slash all the way through it. That also represents phi. So r is rho sine of phi. So to get x, I simply replace r with rho sine phi, then multiply by cosine theta. Same thing. Y is r sine theta, so I replace r with rho sine phi, and I get sine theta. To get z, I have to use the relationship that z is rho cosine of phi, and that will do it. Now, if I want to go in the reverse direction, I can do that by saying that x is equal to this, y is equal to that, z is equal to that, and of course, we still know from before that x squared plus y squared plus z squared gives us rho squared. If we want to go from rectangular to spherical, so I have rectangular, I need spherical, I want to go directly, then I have this x squared plus y squared is z squared gives me rho squared. The tangent of theta being y over x will give me the angle theta. And then phi is the arc cosine of z over rho. Let's go ahead and take a look at example 3. In example 3, we want to take the point in spherical coordinate system and describe its location in both rectangular and cylindrical. So we want to go first from spherical to rectangular, and then we can go from spherical to cylindrical or from rectangular to cylindrical, whichever way you want to go. So go ahead and pause the video, work it out, then turn the video back on, and we'll compare our answers. So the first thing I did was I went ahead and I labeled the spherical coordinates rho, theta, and phi. That way I could keep straight which one is which. X is r cosine theta, r is rho sine phi. So I replace rho, phi, and theta with what they're equal to from the ordered triple in spherical coordinates and work out the arithmetic to get negative √3 divided by 2. I do the same for y, but y is r sine theta, so it's rho sine phi sine theta, and that gives me negative 1/2. Z is found by projecting into the YZ plane, and this tells me that Z is equal to rho cosine of phi, which gives me √3. This gives me the rectangular coordinates, negative √3 over 2, negative 1/2, and √3, which are the same point in three-dimensional space as the spherical coordinates 2, negative 5 pi over 6, and pi over 6. Now we want to take the same point and we want to convert it into cylindrical. When we're converting into cylindrical, we can use the relationship that r is rho sine of phi, which we actually already computed as part of the previous problem, is 1. Theta does not change, so it will remain negative 5 pi over 6. And again, we've already computed z in the previous one. So in cylindrical coordinates, the same point is 1, negative 5 pi over 6, √3. Notice that there's nothing to indicate in any of these which coordinate system you're in. You have to be told, or you have to write a note so that you know which system you're now in. This answer is now in the cylindrical system. Let's take a look at example 4. In example 4, we want to convert this point from cylindrical to spherical coordinates. And let's see, in example 5, we want to convert the point from Cartesian to spherical. Go ahead and pause the video to work these two examples out, then turn the video back on so that we can compare our answers. So again, the first thing I did was label the different parts with their variables. We're starting from cylindrical, so this is r, theta, and z. R is square root 6, theta is pi divided by 4, z is the square root of 2. To convert into spherical, I use the relationship from the projection into the YZ plane that r squared plus z squared equals rho squared. And that tells me that rho, being from 0 to infinity, positive value, is the square root of 8, or 2 square roots of 2. Theta does not change between the cylindrical and the spherical system, so it remains pi over 4. To find phi, I take the inverse cosine of z divided by rho, which means I have to already have rho in order to compute it. I computed rho to be 2 square roots of 2, and z is the square root of 2, which gives me which gives me 1/2, and the angle whose cosine is 1/2 is pi over 3. And so this gives me the spherical coordinates for the same point of 2 square roots of 2, comma, pi over 4, comma, pi over 3. Let's now take a look at example 5. In example 5, we're going from the Cartesian system or the rectangular system into the spherical system. So I label the points in my ordered triple as x, y, and z. -1, 1, negative square root of 2. I know that in the spherical system, the relationship is x squared plus y squared plus z squared gives me rho squared. So I square each of the components of the ordered triple to get that rho squared is 4. Since rho is strictly positive, or rather non-negative, I get rho equals to 2. Then I use the relationship that in the projection into the xy plane, the tangent of theta is y over x, to write that tangent of theta is 1 divided by -1. So I need to find the arctangent of -1, but with arctangent, we may not end up in the right quadrant. We don't have to worry about that with arccosine because it's defined over the correct range, but arctangent may not be. The arctangent of -1 is -pi/4. But if this point in the xy plane, the projection of it, is in quadrant 2, then I need to use the angle 3pi/4. And the ordered pair, -1, 1, is in quadrant 2, so I need to use 3pi/4. Finally, I compute my phi by finding the arccosine of z divided by rho again, and this gives me 3 pi divided by 4. Notice that the angle whose cosine is -√2/2, it's negative, so it's going to be in quadrant 2, and √2/2 is one of the multiples of pi/4, so it must be 3 pi/4. So -1, 1, -√2 in rectangular is equivalent to 2, 3 pi/4, 3 pi/4 in spherical. The last thing that we want to do is we want to identify surfaces in the spherical coordinate system. We've identified surfaces in the cylindrical coordinate system, but what do they look like in the spherical coordinate system? So the first one I want to start with is a sphere. Now, if I want to plot it so that it's in the spherical coordinate system, remember that's rho, theta, and phi. How do I do that? So one of the things that I can do is I can select an implicit surface. So let's go out to CalcPlot 3D and let me see if I still have this particular one open. Not that one, or that one, this one. All right, how did I know it wasn't that first sphere? I looked at the equation. If I type in rho equals 4, and again, I'm using this box down at the bottom of the implicit surface menu to type in rho, or I could type in RHO equals 4. When I hit enter, it's going to change the XYZ to rho, theta, phi. Make sure that your phi extends in both directions and your theta is 0 to 2 pi and your phi is 0 to pi. And then you should get the whole thing. All right. So again, that's done by selecting implicit surface, clicking inside the box, and here it is, and then clicking on rho. You'll have to take out the automatic equation that it puts in. This is what happens when we hold rho constant, but we allow theta and phi to vary. We get a sphere of radius rho with the center at the origin. Now, if we hold the angle theta constant while rho and phi are allowed to vary, we should get the same half plane that we got in the cylindrical coordinate system because theta is the same in both systems, and indeed we do. How do you enter this in CalcPlot 3D? Again, click in the select box and then choose implicit surface. Delete the equation that's supplied automatically, click on the symbol for theta and type in theta equals whatever the constant is, here pi divided by 4. And this will give you the half plane. Remember, theta is measured from the positive x counterclockwise to the projection of the point into the plane. What if we hold the angle phi constant and allow rho and theta to vary? If we hold the angle phi constant, remember phi is measured from the positive z down. If I hold that constant, it traces out one nap of a cone, of a double napped cone, or what most people think of when they think of a cone, they actually think of one nap of it. So it traces out one nap of it, and it gives you the half cone. How do you put this into CalcPlot 3D? Again, click on Select, choose Implicit Surface, delete the equation that's automatically supplied, select the symbol for phi from the bottom menu, and type in the constant that phi is equal to. You'll see down here the different shapes that we can get in the spherical coordinate system. The sphere, when we hold rho constant and let theta and phi vary. The half plane, when we hold theta constant and let rho and phi vary. And the two half cones that we get if we hold phi constant and allow rho and theta to vary. If the constant is between 0 and pi over 2, it's the upper cone. And if the constant is between pi over 2 and pi, it's the lower cone. This is the end of this particular section and the end of this particular chapter. In the next chapter, we'll be looking at chapter 3, and I hope you'll join me there. We're going to start with a section that isn't technically in the book. We're going to be talking about how to parameterize lines and vectors in three-dimensional space.